So, okay, I'm going to talk about understanding the role of memorization in learning broadly, but also in the context of deep learning. Of course, that's why I guess you're here. You've heard deep learning somewhere in the abstract, perhaps. Anyway, so the starting point for this work is this following well-known empirical phenomena in which deep learning networks which achieve, or algorithms which achieve state-of-the-art performance in text and image data tend to fit the training data very well, often perfectly. And this is true even in the cases where the true generalization error or the test error that we measure is actually quite high, such as in this typical example, where the training error is 0, but the test error is around 50%. So the reason why this is strange and somewhat puzzling is that most data sets contain at least some non-trivial fraction of noise and outliers, examples that cannot be predicted by the learning algorithms. So the only way to fit those examples is to effectively memorize the labels in the data set. And for now, I'll be talking of memorization as informally, as specifically this phenomenon in which examples that cannot be predicted are still fit. So, in fact, we now know from the famous experiments of Zhang and others that deep learning networks would fit even completely random labels. For example, in their experiment on this very large data set ImageNet, which has more than 1 million examples labeled in 1,000 classes, the standard deep learning algorithm was able to fit most of the data. It achieved training error of just 9%. Even though the labels were completely random. And of course, it didn't learn anything useful in the process. So the actual test error was nearly 100%. So this is sort of a puzzling empirical phenomena. But the reason why we are interested in it is it also kind of goes against our classical view of learning. And let me be a little bit more precise about what I mean by this. So the standard view of theory starts with of analysis of many learning methods, starts with this kind of standard decomposition of the generalization error of a learning algorithm, which we'll denote by this H hat, the model output by algorithm A on some data set S, and we'll decompose the generalization, the true error of this model into empirical error and just the difference between the empirical error and the true generalization error. This is just obvious decomposition. And we'll refer to the second part is usually referred to as generalization gap. Of course, this part cannot be measured explicitly, but it can be often bounded, kind of its worst case value or ability, the worst case ability of the algorithm to overfit data. It can be often bounded via different proxies, and you've all heard about those, or most of you have heard about, such as via notions of EC dimension or the macro complexity, stability, peg base, and so forth, and so on and so forth. So now, given such a proxy, sort of the standard way to design an algorithm, which would kind of follow this rule, is to design an algorithm which will minimize some kind of balance between the empirical error and some lambda times the value of this proxy. And in order for this sort of actually to give you an upper bound on generalization error, this lambda has to be at least 1. Otherwise, it won't upper bound the error. So the algorithm might end up being suboptimal. However, if you think about it for a second, in order to fit a completely noisy label, completely random label, or an outlier which has 0 probability, you actually need to set this value of lambda has to be at most 1, basically because you don't learn anything useful, so the ability to fit data has to grow by 1 for every such example that you fit. So the price you pay in increasing this generalization gap is at least as large as what you gain in the empirical error. So at best, you could say that the standard approach will not explain fitting of data. In the worst, it actually kind of, you could say, it suggests that what we're doing is wrong. Like it is a suboptimal way to learn, which of course we don't think so, because again, these are our best algorithms. And we would like to understand why do they kind of go against this wisdom, or why are they not explained by the classical approaches. Let me mention that these are sort of, for those who have been around for a while, these are not new questions. The questions about why boosting and bagging algorithms together with some decision lists fit data perfectly have been around for over 20 years, and people who have seen this result many people who have seen this result in the context of deep learning were not surprised. But that only means that, okay, it gives us even more reasons to answer that question. In fact, our answer will not be in any way kind of very specific to deep learning, and we'll see that it actually explains this phenomena more broadly for all algorithms. Let me also briefly mention that in addition to sort of intellectual reasons to answer this question, there are also more practical ones in the context of privacy. You can think for a second about training a model on sensitive user data, such as their health records. This kind of tendency to memorize everything in the data set is likely to create models that leak more information about the user data, something that we often want to avoid, at least at Google. And as a result, the question of whether you can still learn well but without memorizing is of practical importance. We don't want to be memorizing. Question, can we still achieve state-of-the-art performance or not? So the question, I hope, is clear, and why it's puzzling, I imagine, is clear, unless there are, okay. Feel free to always stop me and let me know if you have any questions. So let me briefly mention what sort of, there's a lot of theory of generalization has been done, kind of some of it actually motivated by the same puzzling questions. Let me briefly mention why I think existing work doesn't quite answer the question that we're posing here. So a lot of the work motivated by this question looks at new ways to bound that same generalization gap to come up with a different notion, different proxy, sometimes explicit, sometimes implicit by an algorithm. As an over-parameterized regime, you kind of have to have some kind of either explicit or implicit regularization. And as mentioned, these all work just follow the same classical approach, and they won't be able to explain this phenomenon of memorization. Perhaps closer to, actually quite a bit more closer to our work is this line of work on understanding generalization properties of interpolating methods. And a method is referred to as interpolating specifically if it fits the training data perfectly. And most of this work shows that there exist methods that interpolate and still achieve the same sort of the best generalization bounds we know how to achieve. At the same time, none of these results, as far as I know, show that interpolation gives any advantage. In some sense, in many of these results, interpolation sometimes even suffers some loss as opposed to the best algorithms we have. So these results do not answer the why question. Why should we be interpolating? And it's also worth mentioning that memorization also happens without the kind of phenomena we're talking about happens even without interpolation, such as in the ImageNet example that I've mentioned. The test error was only 9%, not 0%, but we're still obviously memorizing noisy data. So in terms of the work which actually does look at potential advantages of interpolation, one sort of advantage which sometimes is mentioned or maybe confused with advantage of interpolation is advantages over parameterization. We know that over parameterizing the system is useful. It gives us access to a richer set of models as long as we can search better in that space. But while interpolation requires over parameterization, you need to be able to have a lot of degrees of freedom. It doesn't imply it. In principle, we can be in an over parameterized regime, but not, we have the freedom to interpolate the data, but we don't actually do it. So these are not the same. Another sort of advantage of interpolation that has been suggested is that it has some computational advantages based on some evidence in the convex case, which suggests that SGD will converge faster. At least the stated rates are better when all the losses have a shared minimizer. But we don't quite see this happening in practice. We certainly train, even in non-interpolating regime, deep nets essentially as fast as in the interpolating regime. So that's sort of the brief survey of the related work. Let me start now with a very high-level intuition about the proposed explanation for this phenomenon. And for this purposes, let's look at a few examples of the truck class from CFAR 10. These are all real images labeled as a truck. And what's common about them is that they're all hard to predict. If you were to remove any of them from the data set, none of them would be actually predicted as truck. They're also very rare and very different from all other images from the truck. So if everything that you know about trucks is what you saw in the CFAR 10 data set, they are all quite plausibly trucks. The question is, should you actually memorize and incorporate them into your model? Because you cannot predict, you have to memorize their labels. Should you do it or not? And it's not so obvious what the question is. It turns out that the first one of those is useful because in the test set, there is an example which is quite similar, is also labeled as a truck. And having that example in the training set, really memorizing the first example really improves the performance on this test example. And similarly, for the third example of this wheel, there is a related example in the test set on which, again, accuracy improves quite a bit thanks to if you incorporate that example. But no improvement have been happened to the other as a result of the other examples on any in the model. So what I mean is it turns out that it is overall useful to memorize. But a priori, without looking at the tests or with a test set or without knowing the data distribution, it might be impossible to tell. So the high-level explanation for why do we end up memorizing noise and outliers is that because we cannot tell them apart from hard, rare, but still useful examples. To make it explain it a little more detail, where do these rare examples come from? And for this, it's useful to understand that natural data is not homogeneous. It's not just one blob of data. It can be naturally thought of as consisting of subpopulations, basically distinct subpopulations of examples which are quite similar to each other, but possibly quite distinct from examples in other subpopulations. Let's, as an example, take a quick look at the images of birds from CFAR 10 datasets. There are 5,000 images, but they cover over hundreds of bird species, and pictures are taken on very different backgrounds, different angles of view, different levels of magnification, and so on and so forth. Many of these subpopulations are quite different from each other, so that if you don't observe any of the representative of these from that subpopulation, and you're not a human who has already seen millions of those, you will not be able to predict accurately on that subpopulation. Because there are so many subpopulations, some of the subpopulation will have only a single representative. And for that representative, because it's a single one, you cannot really distinguish it from an outlier, something which is really has maybe mass zero over in the true distribution, because those will also occur exactly once. And similarly, if that example is hard to predict, you won't be able to tell whether the example is noisy or not. But the main effect that we'll be looking at is that these examples from a subpopulation whose frequency, the true frequency is around 1/n, the ones from which you'll have likely to have only a single representative, will be hard to distinguish from noise and outliers. So of course the question, okay, so these are just things which occur very rarely, maybe we could ignore them all. And then it's the question of how many of those are there in the distribution. And many of you have probably heard that natural data tends to follow so-called long-tail distributions. And these are distributions that tend to have this property that the total contribution of frequencies on the order of 1/n can make up a significant fraction of the whole population, such as in this classical example of the SIP distribution, famously followed by the frequencies of words in the language, in which, again, the kth most frequent element has frequency on the order of 1/k. So for this distribution over capital N elements, if you look at the total kind of weight of all frequency on the order of 1 over n, it will be, this total weight will be on the order of 1 over log capital N. So it could be quite large if the number of, even when the number of population is, again, not so small. So that's sort of I mean, we all heard of those. The question are, do these long tail distributions exist in kind of actual data? And there's some evidence. I mean, practitioners often refer to this informally, but there is also some more formal empirical evidence. And some of it comes in the context of data sets which have additional annotations, such as the SUN data set, in which, in addition to the object class, it also specifies the visibility pattern. What is the angle from which the object is observed? And in this paper by Zhu and others, they have plotted the number of objects with a specific visibility pattern. And you can see it kind of follows pretty much SIP distribution. This is this linear on the log-log scale. And even more concretely, you see that the non-trivial fraction of the distribution occurs exactly once. These are kind of very rare visibility patterns, and similar stuff for both humans and buses. So that's one case in which these long-tail phenomena are known. The other is cases this comes from so-called extreme multi-class problems, in which we have hundreds of thousands different class labels, but we have different number of images or sentences for every class. They are not class balanced. And in these cases, each label is kind of very fine-grained, and many fine-grained labels correspond to one higher level label. For example, again, dog breeds would all correspond to a dog. And in this case, we know that this distribution of labels per class also follows this kind of long-tail distribution there, I think in kind of strange scale, but that's power law distribution with, I think, the constant 1. So that's the reason why I think this kind of long-tail distribution do occur in many natural data sets, both text and image. And let me briefly mention another sort of piece of both empirical support and a bit of an inspiration for my work, and it comes from understanding learning and privacy, something that I already mentioned, and specifically learning with differential privacy. And it's not so important what differential privacy is if you haven't heard about it, but roughly what's important to understand is that by its definition, it prevents algorithm from memorizing rare things, and in particular from fitting noise. So these algorithms cannot memorize, and they don't memorize any noise. They have very small generalization gap, pretty much non-existent. And at the same time, another property of these algorithms, they don't quite reach the state of the art. For example, the best error that I know is achievable on MNIST is around 2%, whereas non-privately we have 0.2%. And some of it may be due to the fact that we don't have the best algorithm for differentially private learning, but some of it, I think, maybe not entirely coincidental. And to understand whether this is true, it's maybe worth looking at what are the examples on which we can predict well, non-privately, but differentially private algorithms fail. And this is exactly what a group of colleagues at Google has done. So they've done on a bunch of data sets. Here are some of the kind of examples from the MNIST data set. So the ones in which differentially private algorithms are very accurate are very prototypical ones. The ones on which they're least accurate are all very rare. They're all still valid numbers 3, but they're obviously very unusual ways to write these digits. And similarly, for example, for planes, you see very prototypical images of plane versus various very rare ways to, at least seemingly very unusual ways to of whatever, having an image of a plane. So it certainly to me suggests that the fact that these rare examples are being missed cannot be memorized is exactly why, at least explain partially why these systems do not achieve state-of-the-art performance. Anyway, so far this has been just a story. I hope you're enjoying it. But let me briefly explain that actually all these phenomena can be captured relatively easily theoretically. So and for this purpose, let me start with a very simple model. So in this case, for simplicity, I'll look, the model will be just focus on just a single phenomena. The fact that things that occur once and are useful, their frequency in the population is on the order of 1 over n, cannot be distinguished from things which are outliers, whose probability is roughly 0, but you still observe them once in the data set. So the model will be kind of pretty simple. We'll have a discrete domain of size capital N, and we'll denote our distribution over this domain by D. We'll assume that there is some true labeling functions. We won't care about noise for now, which belongs to some class of function capital F, which again, we'll just look at binary classification for simplicity. And you can think of capital F as being all the functions. We want to think about some kind of hard learning problems. Problem for simplicity, learning all the function is probably the hardest problem. Of course, the goal will be minimize the true or generalization error of the hypothesis we output on the data set, draw an ID from distribution labeled by this function. And now this question is how will we measure the error of the algorithm? Of course, we cannot hope that the algorithm will be optimal for all kind of distributions and functions. So the standard notion of error would be like the pack learning would be minimizing overall functions and all data distribution. This kind of expected generalization error where expectation is taken with respect to the data set and the algorithm. The problem with this definition, the reason why it won't allow us, won't work for us, is that if capital N is sufficiently large, much larger than n, then all algorithms, no matter what you do, you'll have very, very high error, and basically it doesn't really matter what you do. So this will not work for us, won't capture the kind of phenomena we're interested in. Another typical model is to assume that the algorithm knows the distribution, and then we minimize just the error with respect to that distribution. This also will not work for us, because if you know the distribution, then you don't need to fit the outliers. You only will fit those whose probability you know. Again, does not capture the phenomena we're interested in. So the specific model that we'll actually be using is just a small modification. We'll assume that we know there exists some prior over frequencies. There are some capital N frequencies, pi 1 through pi n, and we'll denote them all by pi. And sort of a tempting way to define the error, and one which actually works, is to define just the minimum over try to minimize the error, which is just the minimum over all functions f as usual, and for a minimum over all distributions that are equal to this pi up to the permutation. So one could look at this notion of error. Turns out it's very complicated to work with, although people did use it in some influential work in the context of density estimation. Instead, we'll look at the simplified version of essentially the same notion, in which we will instead look at the average case over basically this. Either you can think of over all permutations, or we'll simplify it even just a bit further. We'll assume that that each distribution will define the following process to generate a distribution over data points. And according to this process, for every point in the domain, we'll pick a frequency px randomly from this list of all these possible frequencies, randomly and independently, and then we'll normalize. So we'll basically be kind of getting something like a random permutation of all these frequencies. And for this way to define a distribution randomly, we'll be looking at algorithms that minimize the expected error over the choice of a data distribution D from this, according to this process. Yeah. Does the notion of the error make sense? Again, the conclusion that we'll be stating, they do hold for this worst case error, but it's much easier and cleaner to state them for the average case error. So for this notion of error, our sort of main result can be summarized as follows. For every possible algorithm A, its error, this notion of error of this algorithm, will be at least the optimum, the best possible that can be achieved by an algorithm relative to this for this notion of error, plus some term which in which we have first, okay, ignore this tau for a second, we have this the same expectation over distribution and the data set of this error ns of h, which is denotes the number of examples which occur once in S, but the algorithm A, or the hypothesis output by the algorithm A, does not fit them. So we look at all those which are not fit and just count those. And not fitting, just, predicting a different label from the one you see in the training set. And so basically, we're relating here so any algorithm which does not fit will suffer certain penalty. And the value of that penalty will depend on this parameter tau. And tau is actually, that's the exact expression. It depends only on the prior distribution and the value n. And you can think of it as some kind of just a simple Bayesian factor. If you have observed an example once, this changes your sort of prior knowledge about what is the frequency of that example under the distribution. So again, we start with some kind of distribution over distributions. And if you know that a certain example does occur in the training set, this allows you to update your knowledge of the density on that example. And that's exactly what happens. Note that we're kind of not comparing, maybe in more typical models, you would be comparing your worst case, your error, against the best in class or some kind of Bayes optimal. Here we're comparing to, I think, a different criteria, which I think makes more sense, is the best achievable by any algorithm. Basically, in this case, again, it's something that is effectively Bayes optimal. It's very easy to define what it is. So, so that's the main sort of summary of the main result. Let me mention that this tau is very easy to estimate, and it turns out that it's easy to show that it is lower bounded by the total weight of frequencies in the range of 1 over n, for example, from 1 over 2n to 2 over n, divided by n, because we have to kind of normalize, because here we're counting number of errors, and we're comparing it with the expected error. So basically, for distributions such as zip, this value of this tau will mean that the cost you pay for not fitting examples that occur once is high. And it doesn't matter which example of those. Is it an outlier? It doesn't matter whether it's an outlier or not. You have to fit those. And also note that in this case, for now, we are only talking about the benefits of not fitting or not fitting in the noiseless setting. And in this case, the function f, it doesn't even matter. The class of functions doesn't even matter. It doesn't enter this, in some sense, like the suboptimality. Of course, it enters the optimum, but it doesn't affect the price we pay for not fitting. So where the class does start to matter is once we start talking about memorization. And for this point, for the purposes of this work, we define memorization in the following very simple way. For an example for a data set S and an example XY in this data set S, we'll measure memorization of algorithm A on that example as simply as the difference between the prediction of the hypothesis output on data set S on that example and the prediction of the hypothesis on the data set without the example itself, again, on the point in that same example. So if the algorithm is changing its prediction in a strong way, that means that it's, in some sense, effectively memorizing that example because it's, again, changing the prediction after having observed it. So the benefit of this definition is that actually kind of allows us to connect very easily the fitting. It's very easy to connect it to fitting. And to do it, just let's assume that if our function f is sufficiently rich and hard that you cannot, basically your generation error is relatively high, then for many examples in the data set, it's kind of almost immediate consequence of the class being hard, you will not be able to predict well on those examples if you remove the example from the data set. If the problem is hard, most of the specific examples that you see, if you haven't actually had them in the data set, you won't be able to predict them. This is pretty much the same as the generalization error. It happens to be leave one out error. Now, for these examples that you cannot predict, or where you have accuracy of roughly, say, 1/2, the number of in order to be able to fit them, you kind of, by this definition, you have to memorize them. Specifically, the number of errors that we count on examples that appear once is, by definition, is the number of examples that occur once and on which you make an error. And of those, if we restrict ourselves, our attention to those which are hard, on which you cannot predict them without seeing them, then the sum will be exactly 1/2 minus this measure of memorization. Basically, it means that if the problem is hard, you have to memorize a lot to fit, which is kind of obvious. But the point is, we know that fitting is important, and it means that making memorization important for hard problems. Anyway, so far I've only talked about noiseless setting. Let me very briefly mention how one can label noise enters the picture, even though it's not really the main phenomenon here that we're talking about. But let me mention, there are many different models of noise. Let's for a second look at the simplest one, in which we'll be flipping each of the labels we observe randomly with probability eta and independently from everything else. And in this case, again, it's easy to see that if you have an example which you cannot predict without observing, and you observe it only once, then you also cannot, in some sense, condition on observing the label of that example. That label is still the most, as long as the noise rate is less than 1/2, that label is still the most likely label for that example. You observe it only once. So you should still be fitting this label and predicting what you see, even though it's a noisy example. So just plugging this kind of simple noise model into our theory will basically get a result of the following type, where the error that the algorithm will achieve on this noisy distribution will be at least the optimum achievable on this noisy distribution, plus, again, the same term where you kind of have to memorize a lot of stuff, which measures the amount of memorization. The only thing which actually changes is that we have to kind of multiply everything by this factor 1/2 over eta, because sort of noise shrinks the influence of kind of the price you pay for not fitting everything for all the algorithms. Maybe it's not so important what it is, but it is relatively easy to incorporate label noise in this setting as well. Anyway, maybe one I should also make a quick comment is that in this setting where you do have noise, optimal algorithm is no longer interpolation. Basically, for points that you have many copies of, you should be kind of aggregating the noisy labels and trying to figure out the best possible labels. In most cases, you'll not be fitting the same the data set if you want to achieve the optimal error. Anyway, so far this kind of this model captures the phenomenon in the context of very discrete setting, where you should maybe think of every point as representing an entire subpopulation. Let me just briefly explain how you can extend to the more continuous setting, in which basically, of course, every individual point has zero mass. So in some sense, strictly speaking, there is no meaning to fitting an individual point, because it doesn't really affect the prediction at the end. But it is possible, but with some kind of relatively simple assumptions on the algorithm, we will be able to capture these settings as well. And let me give you an example of how this can be done. So, so to do this, we will extend our model in the following way. We'll have still domain X. Now, instead of individual points, we'll have capital N distributions, M1 for Mn, each representing a subpopulation. And for simplicity, we'll assume that they're over disjoint supports. There's some true labeling function, which is kind of constant over subpopulation. It doesn't change over subpopulation. Remember, the subpopulations are parts of a class. So it's also a reasonable assumption. And as before, we'll have some prior over capital N frequencies. And now to create a distribution, our sort of generative process will be a little different. For each index I in this N, for each subpopulation, we'll pick randomly its frequency. Again, normalize everything to 1. and define the data distribution to be the mixture distribution with these random frequencies, again, chosen from the prior prior pi. So instead of mixing individual points, we're just mixing entire distributions. So, and then we define the error exactly otherwise in exactly the same way with respect to the distribution chosen randomly from this prior over distributions. Now to connect, to say something about this type of model, we'll need to make some assumptions about algorithm. Roughly, we want to say that if an algorithm observes, say, a single representative from some subpopulation and makes some prediction on that single representative they have observed, their prediction of that single representative will be correlated with the value that the hypothesis gives to the entire subpopulation. So if you've seen only one, and you're predicting, again, some value, you see a first point in some, say, cluster, you label it, this will affect your prediction on the, somewhat affect the predictions on the entire cluster. More specifically, we call it whatever, a subpopulation coupling. Formally, it's defined as follows. We say that algorithm A is lambda subpopulation coupled if for every data set an example xy in that data set, which happens to be the only representative from some subpopulation mk, the total variation between the predictions of the hypothesis output by the algorithm on that data set, on that example x, and on an example drawn randomly from subpopulations, the total variation distance is bounded away from 1. So there is some kind of correlation between those two. And now once you define it, it turns out this kind of makes fitting important because it affects not just the individual point, but the kind of entire subpopulation. And so we can kind of very easily get the very similar type of result in the setting. The only thing which changes is that now we'll have this lambda, which measures the coupling in the suboptimality term. So as long as you have some non-trivial coupling, you will get some kind of non-trivial price for not fitting. Now let me, I think of it kind of intuitively a very reasonable assumption, but let me also briefly mention that it's not hard to show that it will happen under some reasonable models of data and standard algorithms. For example, definitely for algorithms such as k-nearest neighbor, if you assume that members of subpopulation are quite a bit closer to each other than to other subpopulations, then the first representative of the subpopulation will affect the predictions on the entire subpopulation. Maybe a bit more interesting is that in the context of large marginal linear classification and its VMs, in the over-parameterized regime, very similar effect will happen if, again, subpopulations are sufficiently kind of independent and again, clustered in, somewhat. You can think of it as roughly as something of the following happening if, again, in over-parameterized regime, you will classify everything you'll fit every data point correctly. And if you place one representative of subpopulation on sort of on the right side of the hyperplane, then kind of at least half space around it will also be classified in exactly the same way. And that half space is likely to contain a non-trivial chunk of the subpopulation. Again, assuming these kind of data models, again, the goal here is not to say that this is necessarily how data should be modeled, but that these things are reasonable assumption about algorithm, which will lead to this phenomenon. Okay, so that's all that I wanted to say about theory. Let me now mention some very fresh experiments from an ongoing work with Qian Zhang, in which we kind of try to test the hypothesis, which is suggested both by the intuition and the theory in this work. And at a high level, okay, the basic hypothesis of just to remind you again, is that there will be examples in the training set that occur exactly once, but we cannot tell them from noise. But these examples are useful in the sense that they have non-trivial frequency in the true distribution, which means that some of them will also have to occur in the test set. And of course, the hypothesis is that if you didn't memorize the example, you won't be able to predict well on the corresponding example in the test set. So the hypothesis says, as a result, that there will exist pairs of examples 1 in the training set, Z, and Z prime in the test set, such that the example in the training set has to be memorized to be fit. Basically, the accuracy on that example without observing it is low, let's say not too high. And also the sort of inclusion of the example in the XY in the training set significantly affects the accuracy on the corresponding example in the test set, in this case by, for example, at least by 20%. Again, on average, the influence of one example on the other is tiny or non-existent, but we'll find, our goal is, our hypothesis there exist pairs where this influence is large and the influential example is requires memorization to be fit. And of course, the hypothesis says that there will be plenty of those. So fraction of such example is significant, so the total effect, cumulative effect on the generalization error of ignoring them will be significant. So this is, I think the hypothesis makes a lot of sense, at least to me. One issue with it is that because it talks about pairs of examples, one in training and test set, and it kind of requires each of them, testing this hypothesis is, or finding a very large number of such examples directly is hard. I mean, it's actually, I would say, computationally prohibitive to do it exactly, even on simple data set and even using quite a few computers that we have at Google. So, but the good thing is we kind of, for the hypothesis, we don't need to find all of them. It suffices for us to kind of show that find many candidates. And then once we have candidates, just checking is not as expensive. So kind of this leads to the problem of how can you find good candidates so that you can then later verify. And what we showed there is a relatively simple way to do it. And it's kind of basically by looking at kind of correlations between example, and specifically the method works as follows. We'll take our training set and generate many random subsets of this training set, each containing a relatively large fraction of the training set, say 70%. And we'll train models on each of those subsets. And now we will, for each pair of examples, one in the training and one in the test set, we'll calculate sort of the advantage that example in training set gives on the example in the test set, where the advantage is measured kind of, we just look at the difference in predicting the example in the test set condition on the example in the training set being included in this random subset, minus the accuracy on that example conditioned on it not being included. So now we have many random subsets. In some of them, each training example is included in some of them and excluded in some other of them, roughly 70% included, 30% not included. And we can look at the accuracy on the test example for across all the models that included versus across those that excluded. That's the criteria. We can measure this advantage. Just need to then pick those statistically significant ones among those. And that's the method. It actually is still quite computationally intensive. So it requires training thousands of models. So as a result, we're not using the very state-of-the-art kind of models for training in this purpose, but in these experiments, but that we don't really need. We're using things which have been state-of-the-art not so long ago. So let me describe you some of the results, which I'm quite happy about. So let's start with this very simple and sort of the venerable MNIST data set, where sort of it's so simple you don't even expect to see much memorization. Okay, we know that you can achieve accuracy of like pretty much 100%. And just to remind you, we have 50,000 examples, around 10 classes, and we'll be looking at just running SGD on some simple convolutional neural network, which achieves over 99% accuracy. So we have used this methods to find correlation, and that's what it gives us. These are the pairs, and these are kind of the most influential ones. And first of all, it does find the things that we're looking for. You can see the accuracy that of the example in the training set is very low, so it would need to be memorized. The advantages it gives is quite non-trivial. It's 30 to what in these most influential ones, it's over 30%. It also visually makes a lot of sense. These ones should be helping. They all look kind of weird, kind of unusual in the same way. So we can then look further down the list of those. These are less influential. those for which you have less advantage, so the difference is larger between the images and so on and so forth. This is those where the influence is even larger, but still larger than 10%, or maybe 13%. All in all, we find more than 70 examples where the advantage is at least 10%, and we verify it using kind of the direct method, and it does look like it's roughly like it should be because there is more noise in these evaluations, so things are kind of a little more spread out. That's roughly what one would expect, and again, 70 is not a huge number, but again, we are in a MNIST data set where we're kind of only 100, less than 100 examples are in the game at all, so it's a very easy data set. So let's now jump straight to some more interesting data set. We also did it for CFAR 10, but for simplicity, let's go directly to CFAR 100. Here we'll have 100 classes, same amount of data. So there's many fewer examples per class, so we'd expect to have much more kind of, basically in each class you'll be looking into much bigger fraction of the tail. The tail will have a bigger fraction of the distribution, and even the baseline accuracy of the algorithms that we'll be using is not, is much lower, is 62%. Again, I mentioned not state of the art, but pretty good. So let me show you some of the examples, that pairs that we find. So the ones where you have the largest influence are, as you can see, near duplicates. And one thing we learned in the process is that CFAR 10 has a pretty large number of near duplicates, which they did not detect. And you can see for those, really the influence is pretty close to 1. The advantage it gives is pretty close to 1. And it makes a lot of sense. Of course, near duplicates is the best reason to memorize something. If you're going to be asked the same question, why don't you memorize what you saw very well? Once we look further down, the sort of the lower range of advantages, you see images which are similar but different, maybe like sometimes maybe next frame from a video or something like this, or sometimes not necessarily the same, but clearly again from the same type. If further down the road we get actually things which are again still very similar, clearly from something I would call the same subpopulation or same type, but these are all different images. Anyway, all in all, there are more than 700 examples with more than 10% advantage, which again in this case corresponds to 7% of the test set, which is quite a non-trivial advantage. And again, we verified, and it looks roughly what you would expect. The correlations are, so not correlation, these advantages are quite significant. So that's all that I want to say about the experiment. Let me conclude. So the basic story of this work is that label memorization is not explained by prior work, and maybe it's not hasn't been quite posed in the same way in the prior work as it is here. We do show that there is a reason why these algorithms memorize, and it's based sort of on a new proposal that says that it all has to do with the kind of data distribution these algorithms are facing. We have implicitly or explicitly tuned the algorithms to deal with the kind of distributions that we have, the image and text data set, and these are long-tailed. So maybe the interesting upshot of this theory is that this memorization, which often involves strong fitting of fitting of the data, is necessary for achieving the optimal generalization error for these long-tail distribution. And this conclusion is basically not algorithm specific. We did need some assumptions about the algorithm, such as this kind of coupling phenomena, but overall it's not specific to deep learning networks. It's just I think of those as fundamental phenomena about learning in the presence of long tails. In terms of future work, of course, the hope is that some of these insights will lead to more faithful theoretical models, which do capture the phenomena we observe, and hopefully help us build better learning algorithms. There are also some nice connections and applications of these insights to other areas, such as privacy and fairness. Privacy I already mentioned. Fairness is obviously also related in the sense that humans also have subpopulations. Some of them are better represented than others. So insights might have connections to learning in this context. Let me know if you have any questions, and thank you.